This video is for those wanting to understand how the International Space Station is viewable from nearly everywhere on Earth, with the exception of areas above 53 degrees north latitude and areas below 53 degrees south latitude. This video is also meant for those who don't believe the Earth is rotating. Some people believe that the Earth is stationary or geocentric, which is where the Sun and all the other planets, as well as the stars, orbit the Earth. Most people that share this belief think we should be able to feel the Earth moving. Here's a short animation showing the ISS passing over the cities of Currituck, North Carolina, Fairview, Oklahoma, and Salinas, California of North America. The first orbit of the ISS starts over Currituck, North Carolina, and takes 93 minutes for a full orbit, while the Earth rotates 23.25 degrees to the east. This brings the ISS over Fairview, Oklahoma. The ISS continues on its second full orbit, and 93 minutes later, it passes over Salinas, California, after the Earth has rotated yet another 23.25 degrees. To demonstrate the ISS passing over Currituck, North Carolina for a second time 24 hours and 48 minutes after the first pass, I continue to run the animation for another 14 full orbits, which equals another 325.5 degrees of the Earth's rotation. That's one full rotation, plus 12 degrees for all 16 orbits. Notice that the ISS passes over Currituck, North Carolina again, but at a lower maximum elevation angle according to the sighting location website. And according to the listed times, the ISS is observable at 7:00 p.m. on Tuesday the 14th, with a maximum height of 20 degrees rather than the 89 degrees we observed the day before. The shift from the maximum height of 89 degrees to 20 degrees over Currituck in 24 hours and 48 minutes is related to the time it takes for the ISS to complete a full orbit. If the orbit were exactly 90 minutes rather than 93 minutes, the ISS would have passed over that location at exactly the same time and same maximum height. So the extra 3 minutes of time per orbit provides exponentially more sighting opportunities. Here's the ISS sighting location pages listing the dates, times, and elevation angles for the 3 example cities I used in this video. You may need to pause the video to study the information given. I added the degrees in longitude for each location, and all 3 cities are all very close to 36 degrees north latitude across the United States. I also included the distances and the elapsed time for each orbit, so you can check it out for yourself. If you look at an active page on the website titled Spot the Station, you'll see a box where you can enter a city, state, or address so you can find the information you want. There's also a live tracking map on the front page, so you can see a live track of the ISS. And finally, I've included a snapshot of the United States from Google Earth with a description of the track across the country, as well as the math for calculating the distance between degrees of longitude at a specific latitude, in case you'd like to check out the distances for a different latitude north or south of 36 degrees. The distances are different for each degree of latitude. Here's the Spot the Station website, where you can search for practically any city on the planet to find out when the space station will be viewable over that location. Just enter the name of the city, state, or country in the search bar, hit enter, find the blue location balloon closest to the area you're interested in, then click on the blue View Sighting Opportunities link to bring up a list of dates, times, cardinal directions, visible duration, and maximum height. In this session, I searched for a few cities around the world that aren't in any particular order or path, just to demonstrate that there are thousands of sighting opportunities every day. First, I chose Salinas, California. Then Clearwater, Florida. New South Wales, Australia. Accra, Ghana. Uxbridge, England. Then Dubai, United Arab Emirates. By the way, the blue circle indicates the viewing area. I believe the radius is 50 miles, meaning the space station can pass directly above anywhere within that blue circle and still be viewed from the chosen point. For the final location, I chose Punta Arenas, Chile, which is the southernmost point in the southern hemisphere at 53 degrees south latitude. Notice that in some cases over Punta Arenas, the ISS can be viewed as many as 3 times in one day. The same is true for many locations across 53 degrees north latitude. You can also find the live tracking map there, as well as lots of information on viewing directions, photography, and more. This is a screenshot of Skyview, which is an app on my Android cell phone for tracking the ISS, as well as stars, constellations, and the Moon. This is a real-time tracking map maintained by the European Space Agency. As previously mentioned, it can be found at the Spot the Station website. The best time for viewing the ISS is just after sunset or just before sunrise. In fact, the times listed on the website are specifically for those time periods. The reason for those specific periods of time is because those are the only times when sunlight will be hitting the underside of the station, allowing it to be spotted so easily with just your eyes. But for a better experience, use a good pair of binoculars. The edges of this map represents one full orbit of the ISS and 23.25 degrees of Earth's rotation. The Earth rotates 0.25 degrees per minute times 93 minutes equals 23.25 degrees for each orbit. If the Earth were not rotating, the ISS would pass over the same location on Earth 16 times a day because its orbital path is fixed. There's a YouTube channel that tracks the ISS. I like this particular channel because they show the station's location over Earth, sunset and sunrise times, a live tracking map, and a view of the Earth from 250 miles altitude. There are 2 scenarios where the ISS travels both northwest to southeast and southwest to northeast. The first scenario is demonstrated in the following animation. In this scenario, the space station is traveling downward at an angle from northwest to southeast. Then half an orbit later on the other side of the Earth, it's traveling upward from southwest to northeast, and all while orbiting in a straight line. The second scenario is demonstrated in the following animation. In this scenario, the ISS travels over Australia from northwest to southeast. Then 12.7 hours or 8½ orbits later, it passes over Australia again, but this time the direction is from southwest to northeast. If we could see all the previous tracks above the surface of the Earth, those tracks would form a weave pattern. That pattern is created by the station traveling upward on one side of the Earth, downward on the other side, and the rotation of Earth at 15 degrees per hour. The following is a short clip from the Janosch Gaia YouTube channel. I hope I pronounced that right. The video is titled, the ISS orbit visualized on the Equirectangular Projection. This is an image I found that was marked free to use during a Google search for image of the ISS over the Moon. There are a lot of them, and from many different locations on Earth. The Earth rotates half as slow as the hour hand on this clock. You would have to watch this 60-second segment 1,440 times to equal just one rotation of the Earth. Our bodies cannot sense steady motion. We feel acceleration, deceleration, and bumps. And to be more specific, bumps, like what we feel while riding on a rough road in a car, those bumps are nothing more than short and quick changes in motion. It's the same with vibrations, earthquakes, and turbulence. The only difference is magnitude. Our bodies only sense changes in motion. Yeah, watching the hour hand on a clock rotate is like watching grass grow, or like watching oil paint dry. The red circular ring was added to make it easier to visualize the path of the space station in this video. In case you're wondering if the path of the ISS can move like this while the Earth sits motionless, dismiss the thought, because in reality, there is no known force that can cause this kind of motion. Newton's first law of motion states that an object in motion remains in motion with the same speed and direction unless an external force is applied to it. Relative to the Earth's orbital plane, our Moon's orbital plane has been on a 5-degree tilt since at least 2300 BC, when the first lunar eclipse was predicted. The only force acting on the Moon is gravity. If gravity were not holding the Moon in orbit around Earth, the Moon would be speeding off into space on a straight path. The same is true for the ISS. The only forces acting on the space station is gravity and a very slight amount of atmospheric drag. Since the ISS is so close to the Earth, they have to raise the altitude a couple times a year.
Over here we have a map of the world with the trajectory of the ISS. As you can see, we fly like on this kind of map, a sinusoidal trajectory. Of course, in reality, we're flying circles around the Earth. In order to make adjustments to our trajectory, which are basically altitude adjustments, because we always fly in the same angle relative to the Earth or to the equator, the inclination does not change. But if we want to make altitude adjustments, we have to increase our speed. Because of that, the ISS has engines at the back of the ISS, but sometimes also we use cargo vehicles to propel the ISS. For example, the European ATV has such a function, which we call reboost. When the ATV is docked at the aft of the ISS, it can light its engines and we will increase the speed of the ISS, and by increasing the speed we go to higher altitude.
The path of the ISS is from 51.6 degrees north latitude to 51.6 degrees south latitude, also known as 51.6 degrees inclination. We know that the ISS always crosses the equator at 51.6 degrees. Anytime the ISS is directly overhead at or near 90 degrees, the direction will either be in a northwest to southeast or a southwest to northeast direction. This is a view of the top of the orbit at 51.6 degrees north latitude. This provides more time to observe both polar regions. The 51.6 degrees inclination allows the ISS to pass over the majority of the Earth to facilitate maximum observation opportunities. I hope this video has helped to clear things up for some people, and I hope the information was understandable enough to make viewing the ISS a little easier. Have a great day.